bit and make it a little bit bigger. Okay, I guess I'm here for you today. Tell me what I'm doing. Go over the unit circle again. Betcha. You know the unit circle, you'll probably make an A on this test.
If we knew it, why would we even make close to an A?
Sure. You know the unit circle, you're going to have happy and healthy lives. That's even better than an A. So there's the unit circle. And let's talk about where our trig functions are positive or negative. On the unit circle, the x coordinate is the cosine of either the angle formed with that ray or the length of the arc. Because remember, S is equal to R times theta. And on the unit circle, R is 1. So when we talk about values of these trig functions, the first member of the ordered pair is the cosine of that angle or arc length. And the second member is the sine of that angle or arc length. And so we're going to go around here first and decide in which quadrants our functions are going to be positive. Sine is the y, cosine is the x, and in the first quadrant, both x and y are positive. The other trig functions are ratios of those of some type, so all of them are positive here. In the second quadrant, only the y values are positive. So which two trig functions rely only on the y value? Sine and cosecant, those are the only two that are positive here. Okay, in quadrant 3, both x and y are negative. So the only functions that can be positive are the ones that are the ratio of the two negative numbers. Which are those? Tangent and cotangent. Tangent is the y value divided by the x value, and cotangent is the other way, x value divided by the y value. So these are positive because a negative divided by a negative is positive. Now in quadrant 4, x is positive, y is negative. So which two trig functions deal only with the x? Cosine and secant. All the others are going to be negative. Okay, now let's go around here and list in terms of degrees. So I'll spot you this one, that's 0. What's the next one in degrees?
30.
Good. Next.
45.
Next.
60.
And?
90.
All right. You want to keep going around or do you want to figure out these values first? Let's go in the first quadrant. Okay, so now I'm in the second blank. I'm going to put radian measure. So 0 degrees is the same as 0 radians. If you have any angle, even the ones that aren't these basic angles, how do you convert from degrees to radians? Multiply by pi over 180. Okay, so 30 times pi over 180 simplifies to what? Pi over 6. Next one. Pi over 4, right? It's the line y is equal to x. Next one. Pi over 3, and then pi halves. Okay. Now let's list the numbers that go with the quadrant lines, with the x and y axes. So with the x-axis, this is 1, 0, then 0, 1, -1, 0, and 0, -1. Are you happy with those? Now let's go to the 45-degree angles, because at the 45-degree angle, y is the same as x. And what are they? Both of them are square root of 2. So at the 45-degree angle, or pi over 4, all of the x's are square root of 2 over 2, and all of the y's are square root of 2 over 2. Okay, so now I'm going to count 45. I'm just going to add 45 degrees to itself. 45 plus 45 is 90. What's 90 plus 45? 135. 135 plus 45 is how much? And then 180 plus 45? 225. 225 plus 45? 270. And then if you add 45 to 270, 315. 315 plus 45 brings you back to 360 degrees. Now, all of the 45-degree angles, 45, 135, 225, and 315, have that same ordered pair, but here make the y values positive in quadrant 2. So we've got negative square root of 2 over 2, positive square root of 2 over 2. In quadrant 3, both of them are negative. Negative square root of 2 over 2, negative square root of 2 over 2. And in quadrant 4, x is positive. So here it's positive square root of 2 over 2, negative square root of 2 over 2. Happy with that? So what do you know now about the pi over 6s? What's the ordered pair there? What is the cosine of pi over 6? The other way, the x value is bigger. See, the x value is bigger there, so we want square root of 3 over 2 first, and then 1/2. So let's go over to here. What is, oh, we didn't do this one as pi, did we? What is pi minus pi over 6? 5 pi over 6? All right, what is pi plus pi over 6? Good. And then what is 2 pi minus pi over 6? There you go. Now let's count in degrees. I'm going to count by 30s. 30, 60, 90. This one then would be 120. Just going to the dotted lines. 120 plus 30 is 150. 150 plus 30 is 180. 180 plus 30 is 210. 210 plus 30 is 240. 240 plus 30 is 270. Plus 30 gives us 300 right here. 300 plus 30 is 330. All right, so we got all the pi over 6s. Every one of them has to be this ordered pair. And in quadrant 2, x is negative, y is positive. So negative square root of 3 over 2, 1/2. Our next pi over 6 is here. Both x and y are negative. Negative square root of 3 over 2, negative 1/2. And then the pi over 6 here in quadrant 4 has x positive, y negative. X positive, y negative. Okay. Now we're at the 60-degree marks. What's the ordered pair at pi over 3? What's cosine of pi over 3? 1/2, and then the wherever one's a half, the other one is square root of 3 over 2. Okay, so now if I just count by pi over 3, that's 1 pi thirds. So this one's 2 pi thirds. Then that one's 3 pi thirds. Then the next one's 4 pi thirds. And then the next one is 5 pi thirds. And then the next one's 6 pi thirds. All right, so all of our pi thirds are going to have this ordered pair. Back here, y is the only one that's positive, so I get a negative 1/2 square root of 3 over 2. Here's the pi thirds here. Both are negative. Negative 1/2 negative square root of 3 over 2. And over here, only x is positive. So 1/2 square root of 3 over 2. And it looks like I got some empty blanks, so let's figure those out. Let's see. Which pi over 4 here is in quadrant 2? 3 pi over 4. So that's 1/4, 2/4, 3/4, 4/4. That means this one's 5 pi over 4. This would be 6 pi over 4, and that simplifies to 3 pi halves. And then this one is 7 pi over 4. And then finally 8 pi over 4. I got all my blanks full? Can you do all that? What else you want to do? I'll put a blank unit circles up here if you want to grab one on the way out to practice with. There's also some posted on Blackboard. So one of them for later class.
What sections, what's up the order again?
All of chapter 3, all of chapter 4, except 4.5. Yes,
Can you go over the positive, negative functions?
I'm sorry, that drilling. Can you say that again?
The positive functions and the negative functions?
Well, if they're not, the sign in our unit circle, the cosine is the x value. Cosine, I guess, of theta. And the y value is the sine of theta. Right? So in the first quadrant, both the x direction and the y direction, if you were to plot a point, would have ordered pairs that are both positive. In quadrant 2, x is negative, y is positive. So sine is the only one positive there. In quadrant 3, both x and y are negative. Tangent is the only one positive there because tangent is the ratio of sine over cosine, negative over negative. And then in quadrant 4, x is a positive direction, but y is a negative direction. And then the functions listed next to them are the 1/overs. Cosecant is 1 over sine, cotangent is 1 over tangent, secant is 1 over cosine. So they have the same SIGN each time. Or you can remember it again as all students take calculus. All of them are positive here. The ones that begin with S are here, sine and 1 over sine. Take T and 1 over T, calculus C and 1 over C. Okay?
How about if you give us something like the sine of 3 plus L would be determining whether it's positive or negative?
Okay, so if you, a radian is a measure of length around the circle. And these radians that I have here are listed in terms of pi. Well, how big is pi? 3.14. So something that's 3 radians, this is 3.14 radians to here. So something that's 3 radians would just about hit that horizontal line right there. So the sine of 3 radians is going to be a very small positive y value. Whereas the cosine of 3 radians is going to be a negative number, almost equal to -1. So what was my question? What is this? What was where is 3 radians? So 3 radians would be back in here.
So if we went over like the tangent for, I would know.
Okay, so let's write these as pi over 2 would be 3.14 divided by 2. So if I take 3.14 and divide it by 2, that's about, let's see, 2 goes into 3 one time, leave me 11, 2 times 5 is 7, about 1.57 puts us here. And then if I, let's see, this is 3 pi over 2. So if I take that and multiply it by 2, I'm sorry, by 3. 3 times 7 is 21, 15, that's 17, 3, that's about 4.71 to about here. And then this is 6.28. And so your question was what again? Like the tangent of 4. So if we were to approximate the tangent of 4 radians, we said 4.71 takes us to here, and 3.14 takes us to here. So 4 radians. Let me see what 4 radians would look like. If this is 4.7, then it's going to be in here somewhere. And so tangent is going to be roughly the slope of that line, right? The y over the x. And so it's going to be something, it's going to be a positive number because both x and y are negative. And it looks to me like the y value is much bigger than the x value. So it should be kind of a positive number closer to -1. Yeah, positive number closer to 1, since y is bigger than x. Okay? I don't know. I don't have the review with me. Can you read it to me?
It wants us to give the locations to correspond to zero and not. So is that just wanting us to give the exact radian measure of where?
Okay, so this deals with the 6 trig functions, or at least the ones that are quotients. Okay, so you should know, you need to know the domains, what x's make sense, and the ranges of the 6 trig functions. In particular, the ones that have the vertical asymptotes. So 4 of our trig functions have vertical asymptotes. You need to know where they are. So that's essentially asking a question about, do you know their domains? So firstly, our sine and cosine functions aren't broken up in any way, shape, or form. So their domains are the set of the real numbers. What do the values of the sine and cosine look like? What kind of values do we get when we take the sine or cosine of a number? Positive, negative, how big? So I can get the cosine of a number to give me 4? We're on the unit circle. Cosine and never is bigger than 1 and is never smaller than -1. So the range of the cosine and the sine are outputs between -1 and 1. Which trig functions have a sine in the denominator? Cotangent and cosecant. Cotangent and cosecant have a sine in the denominator. Oops, not cosecant. Yeah, it is cosecant. It is cosecant. Cosecant and cotangent have a sine in the denominator. Right? So I have some places where this fraction involves dividing by 0, which is the big no in arithmetic, right? Can't divide by 0. So geometrically, those show up as asymptotes. Those are numbers that are not going to be in the domain of these functions. So tell me where these asymptotes occur. For what values of x will the sine be 0? 0. Keep going. Pi, 2 pi, 3 pi, 4 pi, any multiple of pi, any integer multiple of pi. So the domain is x cannot be any integer multiple of pi. All right, so we're in math. We have to be able to express that sentence in terms of the general integer n. How do I write x is not an integer multiple of pi, using n to represent any integer? X is not equal to n times pi. That's the domain. Okay, so that's for the cosecant and the cotangent. Let me list the ranges separately because they have different ranges. But they have the same domain. Now the range of the cosecant. Remember how we graphed the cosecant? We graphed a sine curve, and then everywhere that thing hit the, where the sine curve crossed the x-axis, we do the dotted asymptotes. And then what? Then what did the rest of the cosecant graph look like in between the asymptotes? In between the asymptotes, the cosecants were either parabola type shapes opening upward on the top peak of the sine or opening downward on the bottom peak of the sine. And those peaks had their maximum values at 1, which means my cosine is not going to hit any value between 1 and -1. It only gets values beyond 1 and beyond -1. So the range of the cosecant is from -infinity to -1, and then again to -1, I said, and then again from 1 to infinity. There's no such thing as a cosecant of an angle equaling a half. It can never happen because of the way the cosecant was defined, 1 over the sine. The cotangent was the cosine divided by the sine. Cosine can take on any number, and sine can take on any number except 0. But when sine is real close to 0, cosine's real close to 1, divide a number close to 1 by a number close to 0, and you can make that as big as you want it. Take 9/10 and divide it by 0.000001, and you've got 9,000, maybe. I don't know how many zeros I put there behind the decimal. But I can get the cotangent as large and positive or as large and negative as I want. And the cotangent can also equal 0 because it has a numerator that's a cosine. So cotangent will cross the x-axis wherever cosine is 0. So the cotangent has as its range all real numbers. Then the other two that are left would be the secant and the tangent. The secant and tangent both look like something over a cosine. So those will have asymptotes wherever the cosine takes on a value of 0. Where are those places? Multiples, odd multiples of pi over 2, right? Because even multiples of pi over 2 would cancel the 2's and be at multiples of pi. So we need to throw out odd multiples of pi over 2. X cannot be odd multiples of pi over 2. So here's your chance to write that in terms of the general integer n. Sorry, I missed that. Did it come from you? I can't see your lips move. X cannot equal pi over 2 times 2n plus 1, right? If n is any integer, 2 times n makes it even. 2 times n plus 1 makes it odd. So we say an odd number looks like x is not equal to any odd multiple. 2n plus 1 makes a number odd times pi over 2. The secant behaves like the cosecant. We drew those little parabola-looking shapes wherever the cosine had a 1 or a -1. And so the secant can't take on any values in between -1 and 1. It could take on things smaller than -1 and bigger than -1, or bigger than +1, but nothing in between. Secant is never equal to 0. That's right. And the tangent and the cotangent have the same range. Okay. All right, so if you know where the asymptotes of the tangent of x are, if you know this, and I ask you something like this, where are the smallest positive asymptotes for, say, the tangent of 2x? What does the 2 do to the graph of the tangent of x? Not when I put it inside. Makes the period smaller. So what's the period of the tangent? Where are the two? Tangent of x has asymptotes at every multiple of pi. So if you look at the graph of tangent of x, if you're reading from left to right along the positive x-axis, there's an asymptote at x is 0 and at x is pi. So this will keep the asymptote at x is 0. Where does the asymptote at x is equal to pi move over to? To pi over 2. So we would say at x is 0 and x is pi over 2. Or in particular, this has asymptotes not at any multiple of pi, but any odd multiple of pi over 2. We've moved them smaller. The period is smaller by a factor of 2. Yes.
Sorry, the name of the tangent, same as the secant.
Yes. Secant and tangent both have a cosine on the bottom, so they both have the same domain. They just had different ranges. Okay. Every trig function has a period of 2 pi except tangent and cotangent. Their asymptotes are pi radians apart. Tangent and cotangents, they have a period of pi. All the other ones have period equal to 2 pi. They complete one cycle of their graph and obtain all of their output values in an interval of length 2 pi. Another example like that last one, okay. I've got a critter here. What is this thing? It's jumping. It's flea-like, but spider-like. So if you guys start itching. We are in the biology building. We expect those things to be hopping around. In math, we just have those massively large cockroaches. As a graduate student at College Station, there's a school down there somewhere. And I moved from Tennessee. I never seen cockroaches as big as I saw down there. And they could fly. So I thought, this is a nightmare.
We had those in Argentina too.
Oh, they were nasty. They were nasty because our offices were in the basement because we were mere graduate students. We were just down there with the cockroaches and dead bodies, probably. Gives me the heebie-jeebies. Give me the heebie-jeebies. Let me see if I can make up another one similar to that. Okay. Okay, so we know that f of x is equal to the secant of x has vertical asymptotes at x is equal to, so we're going to fill that blank in. And so f of x, say, is equal to the secant of maybe x over 2 has vertical asymptotes at x is equal to what? So we remind ourselves that the secant of x is equal to 1 over the cosine of x. And so the secant of x over 2 is 1 over the cosine of x over 2. And what causes asymptotes to happen is the division by 0. So let's make a list of some of the places where the cosine is going to be 0. Pi over 2. So plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. That's what we mean by all odd multiples of pi over 2. All right, so we wrote that as pi over 2 times 2n plus 1, where n is any integer. So what does dividing by 2 do to the period length of the cosine curve? It makes it longer now. Instead of having a period from 0 to 2 pi, cosine of pi over 2 has a period from 0 to what? 4 pi. So what? What number has to go in here to make that equal to 0? Well, let's just draw the cosine of x over 2. The cosine of x over 2, you said, has a period of 4 pi. So it does one cycle of this from 0 to 4 pi. That middle point there has to be the middle point of this line segment. So this has to occur at 2 pi. That means this 0 is the midpoint of that line segment. So that's going to be at pi. And then just counting over with symmetry, this would be 3 pi. So it looks to me that if I draw now my secant curve, that's where the asymptotes are going to be. Right? So these are going to have vertical asymptotes at plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so on, or odd multiples of pi. Pi times 2n plus 1. So instead of memorizing, you can kind of rationalize where these asymptotes are going to occur. If any of what I did made sense, otherwise just memorize. If a number makes a period longer by a factor of 2, then it's going to move the asymptotes away by a factor of 2. Okay.
So say that is 1/2 or 2 instead of 1/2.
That's right. So it would do this if this were a 2 instead of a 1/2, then I would label this pi. And this would be 1/2 pi. And then these asymptotes would be at the fourths. Okay. So are you thinking that the graphing is what's going to blow your mind? Everything else is good? Can you convert from degrees to radians?
Yeah.
All right. Convert 220 degrees to radians. And reduce your answer. And then convert convert 5 pi over 9 to degrees. You think you got them? You think you're done converting? I also want you to tell me in which quadrant a 220 degree angle is and a 5 pi over 9 radian angle is. Tell me which quadrant they're in. Nice chair for a classroom. I have a chair that's nice in my office. Can somebody carry this chair back to my office for me? That'd just be borrowing. It's still on university property. I know, why am I sitting down? Just trying to not jump into your problems. All right, let me do the conversion for you. To convert from degrees to radians, there are pi radians in 180 degrees. So that will cancel the degrees. We can cancel the zeros. And then look at 22 over 18. Both are even numbers, so I can divide them both by 2 and get 11 pi over 9. Good? What quadrant is 11 pi over 9 or 220 degrees? Quadrant 3, because this is larger than 180, but smaller than 270. That's what I mean. It's good to know your unit circle, what those degree lines are. So this is in quadrant 3. So cosine of 220 degrees, positive or negative? Negative. Tangent of 220 degrees, positive or negative? See, it's a fun game to play. All right, now we're going to go the other way. Flip this upside down. To convert from radians to degrees, we multiply by 180 over pi. Then the pi's cancel. 9 goes into 18 twice, so this is going to leave me 20. 5 times 20 is 100 degrees. Quadrant which? Quadrant 2. Is the sine of 100 degrees a positive number or a negative number?
Positive.
Good. Cosine?
Negative.
Good. Tangent?
Negative.
We don't care about the rest. All right, so you're good on that. That's a giveaway problem, right?
Yeah.
Good.
Entire test.
entire test. Okay, let's know our unit circle. Find exact values. Give me the sine of 4 pi over 3, the secant of 7 pi over 4, the cotangent of 5 pi over 6, the tangent of 17 pi. Let's see, which one I got? I need a cosine. Cosine of negative 7 pi over 2. I'm missing one. Which trig function am I missing? Cosecant? Cosecant, let's do another negative angle. Let's go with negative, I want to do it over 6. How about negative 15? Nope, that reduces. 16, 17 pi over 6. We can. Maybe. Are they up there now? Nope. A little bit more. How about that? That's a negative 17 pi over 6 for that last cosecant here. So I want this kind of question to be just as easy for you as the converting from degrees to radians type thing. I don't want this to bother anybody. I want this to be an easy question for you. Because all you have to do is know that part of the unit circle and then figure out what quadrant these are in. No, you're going to give me the exact value. The values come from knowing the points on the unit circle, but you only have to know the ones in the first quadrant. My reference angle here is a pi thirds, a pi fourths, a pi sixths, a pi halves, pi sixths. So if you know the ordered pairs at those, that's going to be part of the answer. Now you just have to figure out plus or minus. And of course, the reciprocal identities for the trig functions that aren't the sine and cosine. They bought them, but they won't use them. So if you need one of these, take it home with you. Now I feel like a teacher. Look. I can do that. Or I can conduct. I could wake you up. Who's asleep? Like that. I could play small pool. So it's $1 for every value you miss, 50 cents for getting the value right, but missing a sign. That's how much money I make today. I don't care if you rationalize or not. Unless it's a multiple choice problem, you should know how to rationalize to recognize that I'm multiple choice. It doesn't hurt to practice. Prettier. Are you ready to check? No? I guess I'll sit down again. How do I know 4 pi thirds is in quadrant 3? How do I know that? It's bigger than pi, right? It's pi thirds bigger than pi, so it's in quadrant 3. Sign is negative in quadrant 3. And I know the sign of pi over thirds is square root of 3 over 2. Is that what you got? Okay. Secant is 1 over the cosine. And I know the cosine at pi over 4 is square root of 2 over 2. Now I just have to figure out what quadrant we're in. But that's going to be in quadrant 4 because that's not quite 8 pi over 4. Where 8 pi over 4 would be 2 pi, right? So that backs me up 1/4 into quadrant 4. Quadrant 4 is the secant a positive or negative number? It's positive. So all I gotta do is simplify this. And I get 2 over the square root of 2. Or if you rationalize that by multiplying by square root of 2 over square root of 2, that'll give me a 2 on the bottom. It'll give me a square root of 2 on top. So the secant of 7 pi over 4 simplifies to a positive square root of 2. Cotangent of 5 pi over 6 is going to be the sine of 5 pi over 6 divided by the cosine. Oops, got it backwards. Cosine of 5 pi over 6 divided by the sine of 5 pi over 6. So before I worry about positive or negative, cosine of pi over 6 is square root of 3 over 2. Sine of pi over 6 is 1/2. The halves cancel, leaves me a square root of 3. 5 pi over 6 is not quite pi. So I know that's in quadrant 2. And in quadrant 2, cotangent is going to be negative. So negative square root of 3 is the next value. Tangent is 17 pi, boom, 0, because tangent has a sine on top. Sine of any multiple of pi is 0. Right? Sine of any multiple of pi is 0, so tangent of any multiple of pi is 0. Cosine of 7 pi halves, or negative 7 pi halves, or pi halves. What's cosine of pi halves? Cosine of any pi halves is 0. Right? Cosine of any odd multiple of pi halves is 0. That 7 is odd. Cosine of an odd multiple of pi halves is 0. Cosecant behaves like 1 over the sine. So this is going to be 1 over 1/2. Sine of any pi over 6 is 1/2. Now I got to figure out whether it's going to be a positive or a negative. So now we got to do a little bit of thinking. So let's see. 18 pi over 6 would be 3 pi, right? But it'll be negative. So this is not quite negative 3 pi. So I'm going around the circle backwards. That's negative 1 pi, negative 2 pi, that's negative 3 pi. So that's not quite to negative 3 pi, which means it's back here in quadrant 3. In quadrant 3, all of my trig functions except for tangent and cotangent are negative. So negative 1 over 1/2 is a negative 2. How many of you got all 6 of those right? Yeah, don't even show up for the test tomorrow, Tuesday. Don't show up tomorrow at all. Good? Okay. Next, do it backwards. Can you give me all values of S in the interval, say from pi to 2 pi, for which the secant of S is equal to, I'll make it easy, one that we just did, 2. We have all S, which is arc length, right? Radian measure. And the interval, which is the bottom half of the unit circle, for which the secant is a positive 2. Well, secant's not going to be positive anywhere in quadrant 3. So I can narrow this down and make this go from 3 pi halves to 2 pi. There's only one value in there that the secant is going to be positive. And where is the secant going to be 2? Well, if the secant's 2, what's the cosine? 1/2. Cosine is 1/2 at which reference angle? Pi over 3. So I need the quadrant 4 version of pi over 3. Well, go to 2 pi and subtract pi over 3. 2 pi is the same as 6 pi over 3. So 6 pi over 3 minus 1 pi over 3 gives me 5 pi over 3. Okay. Let's do one more of those. How about all S in, I don't go, let's keep the same list of S's from pi over 2 for which the cosecant of S is a negative 2. Well, now there's a couple of them, right? Because the only places that the cosecant is positive is quadrant 2 and quadrant 1. Between pi and 2 pi, we're in quadrants 3 and 4. So there's 2 values of S that satisfy this relationship. Cosecant is 1 over the sine. Again, if cosecant is 2, then sine has to be a half, right? Where is sine a half at the reference angle? Give me the reference angle I'm going to be using. Pi over 6. So we need the quadrant 2 version of pi over 6 and the quadrant 3 version of pi over 6. So our reference angle is pi over 6. So we know I need to go from pi and add pi over 6, and from 2 pi and subtract pi over 6. So pi plus pi over 6 is 6 plus 1 6 is 7 pi over 6. And 2 pi minus pi over 6, 2 pi is 12 6 minus 1 6 gives me 11 pi over 6. So those are my 2 values of S. Okay? Is that too fast? All right. Given the picture in number 12, the radius of a circle is 15 units. The angle in that arc is 100 degrees. Which of those choices gives you the length S? S is arc length. What's the formula for arc length? Radius times theta in radians. S is r theta, theta is in radians. So your first task is to convert 100 degrees to radians. So you take 100 and multiply it by pi over 180. So you can cancel the zeros, and that gives you 10 over 18 times pi. 10 and 18 are even, so how about 5 pi over 9? But 10 over 18, I said 5 pi over 9. So S is R, which is 15, times 5 pi over 9. None of these choices work, do they? We need pi somewhere. We need a none of the above. Well, let's see. 5 times 5 is 25. 75 pi over 9. So I don't like any of these choices. They must be approximating. It says use a calculator. We're not going to use a calculator. All right, number 14. Do you know how to find the area of a circle given the central angle and the radius? What's the formula for the area of a sector? Theta divided by 2 times r squared. Again, theta has to be in radians. So we have to quickly convert 245 degrees to radians. So we're going to take 245. No, there's not a pi, because this formula comes from taking our pi r squared and take our theta over 2 pi, and the pi from the pi r squared and the theta over 2 pi, pi's cancel. So we're converting 245 degrees to radians. So both of those numbers are divisible by 5. Let's see, 5 times 4 is 20, leave me 45. 5 times 9 is 45. And 5 times 3 is 15, leaving me 30. So that's 49 over 36 times pi. That's our theta. So we're going to take our 49 pi over 36, divide it by 2. So let me just put a factor of a half here, times the radius squared. I'll try to do better numbers than that one. Is that okay? So that's a calculator, that's a calculator. So don't worry about that.
Where does the pi cancel in that?
It doesn't, they've multiplied them out on the calculator. So these are calculator problems, and I'm not going to have calculator problems. Well, you get the gist of the problem, right? You would leave your answer here. Okay, so that was arc length and area of a sector. What else we got going on? Linear velocity kind of stuff. Okay. Let's see, a wheel rotates 35 times per minute. Can you give me the angular speed of the wheel in radians per second? Convert 35 times per minute to radians per second. The radius of the wheel is 20 centimeters. Give the linear velocity of a point on the edge of the wheel. And since this is going to be in radians per second, let's do our angular velocity in centimeters per second. So the first part is simply changing units. And how do you find linear velocity? Take your angular velocity, multiply by the radius. I don't know, 20? 20? So we need to start with 35 rotations per 1 minute, right? For this first part. Take your 35 rotations in 1 minute. Time units always go on the bottom. And now each rotation, one rotation is equal to 2 pi radians. So that gets rid of rotations, it gets radians, but it's now radians per minute. And I wanted radians per second. So what's next? All right, we know that each minute is 60 seconds. So then the minutes cancel and I'm left with radians on top, seconds on the bottom. So I have 35 times 2 pi divided by 60. I can take that 2 and divide it into 60 and get 30. And then both 35 and 30 are multiples of 5. So how about 7 pi over 6? Does that sound good? And that's our angular velocity. Then we said linear velocity is just radius times angular velocity. Gave you 20 centimeters as the radius and 7 pi over 6 radians per second. And so 20 times, oh, I can cancel a 2. How about that? 2 goes into 6 3 times, 2 goes into 20 10 times. So 70 pi over 3 centimeters per second. Okay. Can you do those? So what's left? We covered everything. Well, all right, let's just do some matching. Number 14 there. Number 14, you're supposed to pick out which of the 4 graphs, A, B, C, or D, looks like it would correspond to 1 minus 2 times the sine of x. So let's start here. What does a minus 2 sine of x look like? Upside down, right? Upside down sine curve with an amplitude of 2. And now take this 1. What does that 1 do to that graph? Shifts it up 1. So which of these looks like an amplitude of 2 shifted up 1? Does look like D. See, we'd have to be centered here. That's 2 units this way, 2 units that way, and it's upside down. So D is the correct choice. All right, do you know what the graph of a secant looks like? Has the asymptotes at the pi over 2's, but now if you multiply it by -2, well, the first one does this, the second one does that. So this one occurs between 0 and pi over 2, and this between pi over 2 and 3 pi over 2. Now multiply it by 2, and now multiply it by -2. Any of those look like that? All right, where are these? Any of these have pi's over 2's on them. And it's going to be between this choice and this choice. Which one best describes what I just said? That one's the upside down one, right? Test it out. Secant of 0 is 1. 1 times -2 is -2. Secant of pi is -1. -1 times 2 is a +2. So this one looks like the choice to me. Okay, that's kind of nice. That's a nice little problem, don't you think? The old matching, you didn't like that one? You'd rather draw it yourself? Perfect. I thought matching was nice. Because when you guys draw graphs, you never label things, so I'm left going, what the what? All right. Let's look at problem number 11. And I want you to give me the amplitude, period, phase shift. There's not a vertical translation here, is there? Is there any vertical translation on this one? So you got to be careful. They kind of pulled this 2 out of here to make it look like the problems that are in our book. You got to put that 2 back through the parentheses. So this is y is equal to 3 cosine of 2x minus 2 pi over 4 would be pi over 2. So I want to know the amplitude, period, and the phase shift. All right, what's the amplitude? How do you figure out the period? 2 pi over b. So this one has a period of pi. And when it's multiplied out like this, how do you figure out the phase shift? Negative c over b. So you gotta take that sign. So you can also read that as the opposite of c. So pi over 2 would be the opposite of c. B was 2. What's pi over 2 divided by 2? Pi over 4. Amplitude of 3, period of pi, phase shift of pi over 4. It's positive, so it's to the right. Okay? So it looks something like this. Just for free, no extra charge. Here's the graph. The period has to be pi. We're going to start it at pi over 4. Cosine begins at 1, but this one's going to begin at 3. Then it does this and ends. This one's going to end pi radians away from pi over 4. So what is pi plus pi over 4 simplified to? 5 pi over 4? All right, this point's the midpoint of that. It's halfway between. So 5 pi over 4. I'm going to average these two numbers. Plus pi over 4 divided by 2. That gives me the midpoint, just the average, right? So 5 pi over 4 plus pi over 4 is 6 pi over 4. 6 pi over 4 is 3 pi halves. Divided by 2 gives me 3 pi over 4 here. So these look like halfway in between there. So this would be 2 pi over 4. 3 pi over 4, and this would be 4 pi over 4. 2 pi over 4 simplifies to pi halves. And 4 pi over 4 simplifies to pi. And then the amplitude is 3. Okay? All right. Show me all that stuff next time. Test is in class. If any of you Zooming cannot physically be in class, I need an email from you explaining why not. There's some unit circles up here if you want to practice. There's also blank ones on Blackboard. You don't want to come, that is not a valid reason. A valid reason is if you're not in Lubbock. I want you in class for this one. If you're in Lubbock and you don't want to take it in a crowded classroom, then make arrangements with the testing center to take it in the testing center.
Miss, if I die during the test, everybody else get paid.
Why?
Come on. Work with me.
That's a big sacrifice.
I would be a legend.
All right, stop in the chair here. Put it in the call.